Thank you, and good morning. I am delighted to introduce Dr. Jeff Siegel, this morning's plenary speaker. He and I go back to the 1900s, when we were both graduate students at UC Berkeley. He is a professor of civil and mineral engineering at the University of Toronto and is a Bahen Tanenbaum chair in civil engineering. He holds a joint appointment at the Dalla Lana School of Public Health and the Department of Physical and Environmental Sciences. He holds a master's and Ph.D. in mechanical engineering from UC Berkeley and a bachelor's from Swarthmore. He is a fellow of ASHRAE and the International Society of Indoor Air Quality and Climate. So I was thinking of trying to share an embarrassing story from our graduate school days, but I couldn't really think of anything. But Jeff shared with me, there's that game when you're trying to get to know people, 2 truths and a lie. So here they are. 1, he met Justin Trudeau in 1984. 2, he met the Queen in 1976. And 3, he is related to Stan Getz, the jazz saxophonist. So as you ponder those, let's welcome Jeff to the podium to talk about the secret lives of filters.
So thanks very much for both the introduction and the invitation to be here. What I want to do today is tell a story about filters. And filters are not simple. It's not a simple story, but it's a story that has a lot of interesting pieces to it. And to put things in context, I want to kind of situate filtration within indoor air quality. And so we've known for a long time how to improve indoor air quality, and it's briefly summarized by the 4 things that are on the screen. And some of them have a very long history. Keeping buildings dry. There's a bunch of text here from the Bible that I won't force you to read, but it identifies what to do if you have a moisture problem in your house. And the only comment I'll make about it is the field of mold remediation has not advanced greatly in the past few thousand years. We've also known that source control is really, really important. Get rid of sources indoors so you don't have an indoor air problem. And Dr. Pettenkofer, who was a German hygienist, had a lot of pithy statements about indoor air quality, like the one that's on the screen. And we've known that get rid of the problem before it becomes a problem. Similarly, and from about the same time, we've known how important ventilation is. So these is a couple of chapter excerpts from a book by Catherine Beecher and Harriet Beecher Stowe, 2 sisters, and they wrote this book about the domestic realm. And it was a bestseller in the late 1860s and 1870s in the US. And what strikes me about this book is, there's a whole chapter devoted to indoor air quality. It was seen as being fundamental to having a healthy home. And then another whole chapter on ventilation and how important ventilation is. And there's a tiny bit of aerosol science in this book having to do with venting of combustion as well. And it's just filled with great quotes that indicated that not only did people understand how important indoor air and ventilation were, but it was part of the conversation. And then we get to the subject of today, filtration. And filtration has a much, much shorter history than any of the other items that I mentioned. Filtration was originally largely used in various industrial processes. And then it started, maybe 50 to 100 years ago. It started being used in buildings, but it was not used to protect people in the buildings. It was used to protect the equipment. Things like fans and coils and that sort of thing. And then it was really in the past few decades that we started using filters, thinking about protecting the people in the building. And ASHRAE standard 52.2, which is a very common filtration standard, and I'll talk more about it a little bit later, it's really only a couple of decades old. Its first version was in 1999. And so we really are talking about something today that certainly isn't part of the popular conversation and doesn't really have the history that other things we think about in indoor air. Now, having said that, I think why a filter might be valuable is pretty obvious and pretty clear. We have polluted outdoor and indoor environments. We can use a filter that removes particles by a bunch of different mechanisms, and that filter gets dirty, and it's removing things from the air that people won't breathe in the building. So I don't think it's a hard concept to understand why filters might be beneficial. And if we think about something like COVID-19, there's evidence that filtration can be beneficial. So the graph on the screen comes from data from a study in Georgia, schools in Georgia, where they looked at the COVID case rate, and that's what's shown on the y-axis. And then they just asked the schools, did you improve ventilation, did you use filters, or did you do both? And you can see that the use of ventilation and filtration or in combination reduced the incidence of COVID-19. So that's kind of weaker evidence. And then since then, there's been several papers, like the one I just put on the screen, where do things like put an infected individual with SARS-CoV-2 in a chamber, and then look at the concentrations in the air with and without a filter present. And with a filter present, you get lower concentrations. So, we have plenty of evidence that filters can work. And what I want to do now is kind of motivate at least the first part of this talk by using data from my own university. And so in the summer of 2021, when University of Toronto was going back to in-person teaching, the university made a decision that we're going to follow a procedure that was being promoted by AAAR, among others at the time, and we're going to improve ventilation and filtration in all of our classrooms that are going to be used. And so all of the classrooms had to have at least 6 equivalent air changes an hour, which means you figure out the removal of respiratory particles by ventilation, by central filtration, and if you don't get to 6 by doing that, they added wall-mounted portable air cleaners. And so every space had at least 6 air changes an hour, and the table on the screen is from our chemical engineering building. And this is the classroom Wahlberg 130 that I taught indoor air in that fall, and it was supposed to have 6 air changes an hour. Well, of course, we like to measure things. And so we measured we used low-cost monitors, measured both the CO2 and the particles in several locations in the classroom. And anytime there was a decay that met our criteria for analysis, we looked at what the removal was. And the story is that, there was supposed to be about 2 air changes an hour from ventilation. Instead, we were a little bit less than 1. And there was supposed to be combined everything, ventilation plus filtration, supposed to be 6 air changes an hour. Instead, we were at about 2. So there's this pretty big performance gap. A little bit is coming from ventilation not doing what it was supposed to be doing, but there was a big gap in what filtration was supposed to be doing. And so what I want to do now is talk about why filters don't necessarily do what we think they're doing. So the overall story here is that we think about filters as objects, but really it's the context and how they're used that determines their performance. And so I kind of divide this into 3 bins in my mind. You have to get whatever you're trying to remove from the air to the filter. Once you get it to the filter has to remove it. And then that removal has to compete with all the other loss processes that are happening in the space. And so I want to talk about each of those in a little bit more detail so that you have a sense of what some of the common failures are. So first, getting the air to the filter. This is data from about 50 homes, 3 different studies in different parts of the US and Canada. And what's shown on the y-axis here is something called the recirculation rate. That's how many volumes, house volumes of air go through the filter when the fan is operating in the central system. And what I want you to get from this plot is that there's a huge variation. Some of these homes are having 2 house volumes per hour when the fan is operating, and some of them are having 8 per hour. So right away, there's going to be an obvious difference in a filter installed in those 2 extreme cases just because air isn't getting to it. And it's kind of even worse or more complicated than that. There's also this parameter called runtime, which is how often the fan runs. And runtime, it might not be obvious depending on what types of systems you're used to, but in most of North America, especially in residential and in some types of commercial buildings, the system doesn't run continuously. It only runs when there's a need for heating or cooling. And so a lot of the time, the system is not running because the thermostat is satisfied. So the data that I just put on the screen are from 7,000 homes across North America, measured with a smart thermostat. And each point represents a monthly average in the runtime, how often the fan operates on the y-axis, and the outdoor temperature on the x-axis. And you can see there's a little bit of structure here. Systems run more when it's colder or hotter, which makes sense. But the bigger stories here is, first of all, there is a ton of variation. Some systems at a given set of outdoor conditions run a lot, and other ones barely run at all. And so there's huge variation in this runtime parameter, and even more important is the average. That red dashed line is the median runtime, and it's about 18% in this sample. And that's very, very consistent with other studies that have been done as well. And so what that means is, 80+% of the time, it doesn't matter what filter you have in place, because air isn't going through it. And like I said, this is certainly a residential phenomena, but it's also true in several types of commercial systems as well. And so filtration really, the system really matters. Of course, the filter matters too. And so I think many people here are familiar with filter efficiency curves. They're higher for small particles because of Brownian diffusion, and higher for large particles because of inertial mechanisms. But the reason I wanted to show this picture, in addition to kind of showing that archetypal curve, is because what the authors did here is varied the phase velocity. And so when the phase velocity is high, you get less removal of smaller particles because they don't have as much time to diffuse, but you get more removal of larger particles because they have more inertia. And so why this is important is phase velocities are all over the map in typical HVAC systems, and in many cases they vary as well. And so, the performance you get at any one moment in time is going to be different than in any other moment in time. And this is particularly important when we think about things like filtration standards. So the table I just put up is the main data table from ASHRAE standard 52.2, the filtration standard, and I'll talk more about it a little bit later. But the important thing here is the MERV, the number that we often use to classify filters, comes from an efficiency test, and the efficiency is looked at in 3 different size bins, and based on the efficiency in those bins, the MERV is assigned. Well, the test is run at a specific phase velocity. The phase velocity you have in any real system is going to be completely different, or potentially completely different. And so just because you have a certain MERV, it doesn't mean you're going to get that performance in real life. And here's an example of some in situ filter efficiency results. So this is in 20 homes. This is a MERV 14 filter, so quite an efficient filter. And you can barely see it here, but the black line in the upper right is the standard 52.2 results from a test duct for this filter. And each symbol represents a different home. And what you see here is that some homes perform kind of close to the ASHRAE standard, but a lot don't. And a lot are much, much lower performing. And this is when the exact same filter, when it was brand new, installed in these homes. And there's a lot of small parts of the story. Phase velocity is one of them. But the big part of the story is something really mundane. It's called filter bypass. So we install filters in racks or in slots, and there's often small gaps around the edge of the filter, and very often the filter pulls out of the rack, as you can see in the picture here as well. And so, of course, air is going to preferentially take the easier path, and it's going to go around rather than through the filter. And so it's issues like this that really have only a small amount to do with the actual filter itself and have to do with these issues of installation and maintenance. Then there's another issue that filters change in performance as they're used. So this is the mental model that I think a lot of us have, that this is a filter that was tested in a test duct, and the authors loaded it with standard test dust, as is typically done in filtration standards. And you can see that its efficiency improves as it gets loaded with dust. And that's because what deposits on the filter serves to remove what comes later. So the filter improves in performance. However, a lot of our filters are what's called electret or charged media filters, and these filters don't have that behavior. They often have the opposite behavior. And so what happens is that this is a filter from a commercial building in Finland, and even after a week, you can see degradation in performance, and over time it gets worse and worse as it performs, and so this filter is getting worse over time as it ages. And apologies for the quality of the figure I just put up. It's the only version of it I could find. It's from the first paper I know of on this subject. And the reason I wanted to show this figure is what the authors make very clear is that it really matters with what's on the filter in terms of how much degradation you get. The top panel is isopropyl alcohol. That really gets rid of the charge effects. So you see a big decline in performance. The middle one is a diesel aerosol. And the more diesel aerosol you add, the less well the filter performs. And then the bottom one is a test dust. And with the test dust, this particular filter actually gets better as you load it with test dust. And so all of a sudden we have this problem that this aging effect, it's obviously filter specific, but it also depends with what's being loaded. And that's going to be different in every filter use. And here's a concrete example of that. This is data from the same 20 home study, and this shows the filter efficiency for 4 filters. Each were installed for 3 months in these homes. The lighter colored bar is when the filter is new, and the darker colored boxes are when the filters are at the end of their life. And you can see that all of the filters that have an E, the 3 filters that have an E after their number, those are electret or charged media filters. And they have all declined in performance on average as they've aged, although the amount of decline is very, very home specific. And the one filter, the MERV 8 filter, which was the lowest efficiency filter that we tested, but nonetheless, it didn't on average decline in performance. And so you run into this issue that, this is a very real effect, but how real it is or how important it is in a given application can be variable. And just to make this point really clear, I want to talk about standard 52 too, because it's always fun to talk about filtration standards. And so this is for that same MERV 14 filter that I've showed several other figures for. This is data from the test lab that tested this filter according to the standard. And the standard involves you first doing an initial efficiency test with a polydispersed potassium chloride aerosol. That's the black line on the plot. And then you do 4 rounds of dust loading. As the red lines get darker, that's more and more dust being added to the filter. So this particular filter, a little bit of dust declined. The first dust loading declined the performance. And then as you add dust, it started to pick back up some of its efficiency. And at the end of the day, that's usually where standard 52.2 stops. So when you see a MERV number, it comes from a test like this. However, there is this optional Appendix J, if you want to get into the weeds of the standard, that involves loading the filter with potassium chloride nanoparticles. And this is done to mimic some of the charge losses that we see in at least some buildings. And so the blue shows what happens when the lab did that. They added the potassium chloride nanoparticles, and you can see that the filter efficiency with a little bit of the first loading of the potassium chloride, it declined in performance a little bit, and as they added more and more, it declined in performance further. And if you've ever seen a MERV A or a conditioned MERV value, they're referring to what happens, the MERV from after conditioning. And so this is kind of a contentious issue because it affects some filters more than others, and is this a reasonable conditioning procedure has been a debate at ASHRAE for a long, long time. But I want to show you something here. These are the results from 10 or so of our filters that we sent back to the lab after we took them out of homes. And they just did a quick initial efficiency test. And you can see that every filter that we sent back to them has a different efficiency curve after 3 months. And they all show up in different places in the dust loading and the conditioning. And so it gets very hard to think about how we're going to standardize this effect because it is so variable. And the one comment I'll make from the figure is that the amount of dust or the amount of loading on the filter did not strongly affect where it was in the efficiency degradation. So it's a more complicated effect than just amount of stuff. And it turns out there's a ton of great aerosol science research on what's causing this. And some of the factors that we know to be important are the size distribution of the loading aerosol, how hygroscopic the aerosol is, as well as relative humidity changes in the air, the conductivity of the aerosol, and the morphology of both the particles themselves and of the deposits that form on the filter. And there's a lot of very cool research that looks at things like under some relative humidity changes, some aerosols end up forming dendritic structures on the filter fibers, and those appear to be what's really impacting how much degradation there is. And so, but it kind of underlies the complexity or the complication of this phenomena, which is really important to how a filter performs. So the last point I want to make about filter performance is filter effectiveness. So effectiveness is a concept that's been around for a while, but the idea is you look at the ratio of the concentration with a filter to some reasonable baseline. And here is some data from 16 different studies that looked at filter effectiveness in residential buildings. And effectiveness is on the y-axis. Filter efficiency, as designated by the filter MERV, is on the x-axis, as well as some testing that was done with electrostatic precipitators and HEPA filters in a few of these studies. And, you know, there's maybe a little bit of structure here, but there's not a ton. And so basically what this is telling us is that effectiveness is not just a function of the filter efficiency. It's a function of a whole lot of other factors. And so in some cases you can have a low or maybe a mid efficiency filter that has higher effectiveness than a lower efficiency filter because of these contextual issues. And it's in fact even a little bit worse than that. These are some simulation results that show the efficiency of different filters in kind of an archetypal residential house as a function of the runtime. So the tests I showed you previously were typically done comparing when the fan was running to when the fan wasn't running, and don't account for the fact that the fans only run some of the time. And so what this plot tells us is two things. One, if you have a low filter efficiency, it doesn't matter how much your system runs because the filter isn't removing stuff. But even more importantly, if your runtime is very low, as it can be in some scenarios, your filter efficiency doesn't make that much of a difference because the filter doesn't have a chance to remove things. And we see this in real data as well. These are based on long-term continuous measurements in each of our homes, and this is the effectiveness calculated relative to the MERV 8 filter. And you can see that for all of our filters, including some nominally quite highly efficient filters, the effectiveness is never significantly different from 0 on average in these homes. And there's a lot of reasons for this, but one of the big ones is that the runtime was really low. Over the year, we had a very mild weather year in Toronto, and so our runtime was about 10% on average across all our homes. And so that means that, you know, the filter doesn't matter very much because the system just isn't running. And so all of a sudden, little issues become important, like, does the filter happen to be running when an indoor source is present? And so kind of gets at the complexity. I've talked a lot about central systems, given how much portable filters are being used, especially with COVID. It's important to talk about portable filters a little bit. These are some results from a research group in China where they just deployed portable air cleaners in some homes and looked at their CADR, which is their flow rate times their efficiency, as a function of operation time. And you can see that these filters decline in performance as they age as well. Here, it's somewhat of a charge effect, but mostly what's going on here is a flow effect. As a filter loads, it gets a higher flow resistance. The fan is able to move less air through the filter, and the CADR goes down. And again, it's very specific to what it's being loaded with, how much, and the filter design itself. There's a lot of other issues with portable air cleaners. Noise can be an issue, and that affects user behavior. In many cases, they short circuit, meaning they clean the air locally, not more broadly in the space. If they create airflows, they can resuspend particles from surfaces. And then there's, of course, a big placement issue. If you put filters near a source, you're going to get much better removal of that source, obviously, than if you put them far away from that source. And that's well established in the literature. So just to make this practical, these are my students writing an exam last spring in a classroom that was far, far too small, and that's another story for another day. But this is one of the rooms that use portable air cleaners to get 6 air changes an hour, and you can see the 2 portable air cleaners in the room, and notice that they're kind of on one side of the room. So, you know, that works out great maybe if you're right near those portable air cleaners, but if you're on the other side of the room, you're not getting very much benefit. And so this issue of placement is pretty important. You know, I feel like I've spent the past 20 minutes or so being kind of negative, but I do want to make a really important point. Filtration, you know, does work. And I'm part of a National Academies committee that's reviewing the evidence on the health effects of filtration. And we've found about 69 thus far papers with strong controls that measure a health effect. And generally speaking, there is a health effect associated, a positive health effect from the use of filtration. You know, there's a very consistent message here, although there is also some variation. And so, for example, the environment, the outdoor air in particular, where filters is used, turns out to be important. There is an issue that most of what we have about filters and health effects are very short-term studies, and so some of the long-term health effects are less clear. And the one comment I'll make is that, you know, many of these studies don't even address the context at all. And so, of course, you can use a filter well or you can use it badly. But nonetheless, you know, filters do reduce health effects. There's also a very strong economic argument that can be made for filtration. So these are 4 studies that looked at the benefit to cost ratio for filters, different efficiencies, different methodologies, different types of buildings. But the overall story here is they all found kind of somewhere in the neighborhood of 10 to 100 benefit to cost. Meaning for every $1 we spend on filtration, we get $10 to $100 of economic return. Now, the vast majority of that is avoided healthcare costs. Some of it is in things like improved productivity, reduced absenteeism, those kinds of things. But really, this is mostly about health effects. And so one of the arguments I've kind of made consistently during COVID is that we're leaving money on the table by not investing in filtration. So the story thus far is, you know, pick a good filter, install it well, make sure air goes through it, change it frequently, and make sure it's doing what you think it's doing. So that's the big secret of filtration, is that their performance is related to all these other variables beside the filter itself. But there's a lot of other secrets of filters that are worth talking about. One of them is that filters do a lot of things beside removing particles. So the plot I just brought up is from 4 studies that all looked at the removal of ozone to used particle filters. And you can see that all of them remove ozone to different amounts. And this is not a filter that's designed to remove ozone. And that seems like a good thing, because less ozone in the air. But of course, it's not for nothing, and there's byproducts being formed here. And there is a tiny literature, not a huge one, on some of the byproducts that come from the ozone and other reactions on filter surfaces. And they are very reactive surfaces. There's a lot of stuff from the air that accumulates on them, and that leads to potential formation of byproducts. And one of the comments I'll make is, for those of you who live in homes where you change the filter, you might notice that sometimes the filter smells, and some of that odor is often the result of chemistry. It's also the base filter material itself. This is some research where the researchers were specifically looking at formaldehyde emissions from new filters. And they found quite significant formaldehyde emissions from some filters, predominantly fiberglass filters, as well as filters that were covered with a tackifier, which is a common thing filter manufacturers do to increase how likely particles are to adhere to the surface. And the thing that always struck me about this research is the strong relative humidity effect. And so you get a lot of formaldehyde production from some of these filters, in particular when the relative humidity is high. And so a filter serving outdoor air in a humid time of the year can really produce a lot of formaldehyde. And so filters are doing other things beside just removing particles. Of course, the world of air cleaning is much, much bigger than the media filters that I'm predominantly talking about today. There is a whole bunch of other technologies, some of which I've listed here, and manufacturers make up names all the time, activated oxygen, all kinds of other funny names. The bottom line here, without painting with too broad of a brush, is that a lot of these technologies and a lot of the instantiations of these technologies don't work particularly well. Sometimes they don't work at all, and in some cases there is the potential for the production of harmful byproducts. And so we have this whole industry. Most times I estimate somewhere around half to maybe 3/4 of the industry is involved in these air cleaning technologies that don't really work, don't really have independent tests to verify that they work. And there's all kinds of things manufacturers do to make air cleaning technologies look good. Test in very small chambers, test at very low ventilation rates, report metrics that are non-standard that make removal look bigger than it actually is. So I'll go back to Dr. Pettenkofer again, and he wasn't talking about air cleaners, but the quote is good anyway. This is a suitable place to give a most earnest warning against the use of secret remedies and patent medicines. And I could say a lot more on that, but on the advice of my attorney, I'll move on. The other thing another secret of filters is there's a lot of confusion about the interaction between filters and energy use. And the conventional wisdom that I've heard over and over again, no matter how many times I try and suggest it's more complicated than that, is that if you want to use a better filter, a higher efficiency filter, you're going to have a higher pressure drop. If you're going to have a higher pressure drop, you're going to lead to more energy use. And it turns out both parts of that statement are not quite right. So these are some data compiled by Marwa Zatari of new filter pressure drop in a filter test rig. So this is at a standardized face velocity and as a function of MERV. And there's about 120 or so filters represented in this figure. And you can see that, sure, there's an association there. Higher MERV means bigger pressure drop on average, but there's a ton of variation. And that's because pressure drop comes from velocity that the filter is used at, but in this figure, pressure drop also comes from the design of the filter. You can have a very thin media with high efficiency and relatively low pressure drop, and then pleat it with very deep pleats and get a higher efficiency without the pressure drop consequences. And so there's not a one-to-one correspondence at all. And not only that, it depends on the fan in the system. The fan is what's using the energy here, not the filter, of course. And it turns out that we use many different types of fans and controls in HVAC systems. Very often we have no speed control at all, which means when you use a filter with a higher flow resistance, the flow goes down. When a fan is moving less air, the electricity that it uses will also go down. And so if we're just concerned with fan power, in general, in many systems, a higher pressure drop filter will actually save energy. Now, it's not quite so simple because things like air conditioner efficiency are also impacted by flow. And so the studies that are out there, which aren't that many, show that it's a pretty weak relationship between filter efficiency and energy use, and sometimes even the sign can go either way. Now, some systems do control the speed of the fan, and so the fan has to speed up to move more air through a higher flow resistance filter, and so that does lead to more fan power. But it's really, you can't just say, hey, this is a filter with some pressure drop in a test rig, and then see how that's gonna move on to affecting energy use. Another secret, and maybe this is my secret more than a secret of filters, is everyone's got their fetish. One of mine is dirty filters. And the reason I like dirty filters is they tell us a story about what was in the air. And this is the first article I could find on a researcher who did this, and this was a group in St. Louis in the 1950s, and they used filters in different neighborhoods in St. Louis to say something about what was in the outdoor air. And it's been used in many other times since then. This is some data from a military barracks where they had an outbreak of an adenovirus, and they took samples from the filter and were able to track the outbreaks by looking at what was on the filter over time. And then another interesting paper, this is more recent, this is from a group in the physics department at the University of Washington, and they took the outdoor air intake filters on the physics building and saw the plume from Fukushima Daiichi as it moved over the western US by looking at gamma ray spectroscopy at the filter. And it turns out a few years ago we wrote a review paper. There was maybe 70 or so articles in the literature, and I'm going to guess it's roughly doubled since then. And so, this has been used widely. And what we do is try and make this a little bit more quantitative. And we calculate the average concentration by looking in the numerator at the mass of the filter is collected, as well as the fraction of that's the contaminant that we're interested in. And then the denominator here is a complicated way of getting at the volume of air that went through the filter over its lifetime. And we do things like measure the runtime of the system, measure the flow rate, and have to do some sort of in situ efficiency measurement to be able to get this. But once you have done this effort, you get the kind of time-integrated concentration over the length of time that the filter was installed. And just some examples of this is some data from some homes in central Texas. This particular plot is looking at two groups of fungi. The group in blue is nominally associated with moisture problems. And what you see here is that there's a different fingerprint in each house, and it's even more distinct when you look at the individual fungal species, as well as the fact that there is, in some cases, a seasonal difference that is reflected in what collects on the filter. Even more striking, this is OPEs in the same sample of homes. And you can see two things here. One is there's a very clear fingerprint difference, as well as some very common OPEs in some of these homes, as well as the fact that if you look at the y-axis scales, there's a big difference between the two seasons. And there's this paper, we also look at things like bacteria, endotoxins, phthalates, and you start to see that you can start to pin particular exposures and so on by analyzing the filters. And of course, not every building has a central forced air system. And even if you do have a central forced air system, if you have short run times, that sample that's on the filter might not be that representative of what's in the air. Many commercial buildings and some residential buildings have outdoor air intakes, so the filter is seeing some mix of both indoor and outdoor air, so it's hard to say something about indoor air by just looking at the filter. And so instead we deploy portable air filters, and we analyze the filters afterwards. So this is a picture of filters from a social housing apartment building in Toronto. These filters all came from the same week in the different apartments in the same building. The one with green tape is a blank filter, to give you a sense of what it looked like if it was clean. And you can see, like, you don't have to be an aerosol scientist to say, hey, look, there's something different in the air in these homes. And in particular, the dark brown and some of the other brownish filters, that's tobacco smoke. Those are units that were either smoking themselves or were heavily impacted by their neighbors smoking, as well as kind of a mix of other stuff in some of the other filters. And so when you do that, this is a plot that shows phthalates and across 3 seasons in these homes. There was an energy retrofit in between some of these measurements, so we were particularly interested if the energy retrofit affected concentrations. And you don't see a particularly strong retrofit effect. You don't see much of a seasonal effect. But what you do see is this wide variation between apartments, even in the same, they were all in the same region and in some cases in the same building. You see also an evidence of particular sources. So this is looking at PAHs, and you can see that there is a clear evidence for some of the PAHs in particular of smoking going on in the apartments, or at least a difference between smoking and non-smoking apartments. So you really start to see what's in the air in these environments by looking at what collects on the filter. The last point I want to make today is a really important one, that we should be thinking about filtration in the context of broader equity goals. So these are data, both filter forensics. The blue are from single-family homes in Toronto, and the green are from social housing, multi-unit residential buildings, the study I've showed you thus far. And you can see, and this is a familiar plot in general terms, that shows that there is a pretty big difference, maybe an order of magnitude or two for most of these phthalates in what's in the air between these two environments. And this shows up a ton in the indoor and the outdoor literature. And at some level, I find this, I guess it's helpful to see the difference, but I think we really have to be thinking about what we're doing about it. And I don't want to sound naive. I'm about to sound really naive on the next slide, but I don't want to sound naive by saying filtration is the only solution here. But it is part of the solution here, that some of the particle exposures that are contributing to some of the health disparities we see can be addressed by filtration. And given the money that is spent on healthcare, I think we really have to look very seriously at whether we could further equity goals, improve health outcomes by the use of filtration. And I'm disappointed, especially with COVID, that we haven't done more. And this is the slide where I said I'm going to sound really naive. There are many communities throughout the world that have particular health outcomes or particular exposure hotspots. One of the big ones in parts of northern Canada are pediatric respiratory viruses like RSV. And if you look at the what happens when there's a baby, typically with RSV. These are communities that are quite remote, often fly-in communities. They have to be medically transported, which is an expensive endeavor, to some medical facility to treat them. This is often in Ontario. It's somewhere like Ottawa or Thunder Bay. So that's expensive right there. The medical treatment, and especially the pharmaceuticals, are very expensive. The families have to come along as well, and so the families have to be supported, given a place to live, and supported while they're there for the health treatment. The parents' income is disrupted, and then there's, of course, enormous social costs as well with this. And again, filtration is a small part of what's going on here. There's a lot of issues with housing quality and other systemic issues that are the big part of the story. But my point is simply that simply on an economic basis, we're foolish for not trying things like filtration to, even if we affect a very small number of cases, it more than pays for whatever cost we have. And I hate to say it, but some places in the world do have socialized medicine, and so there is even a raw economic argument to be made for this. So in summary, we think about filters as an item with intrinsic properties, but those properties, and more broadly, the performance of the filter, is as much a function of the context as it is the filter itself. And there's all these positive and negative consequences that arise from the use of filters. And speaking to many of the younger scientists in the room, there's so many unexplored research questions. here on a lot of the details and nuance of what I've said that really are important that we as a community explore. I'll finish by acknowledging, it would be a very long list if I wanted to acknowledge everyone who has contributed to my career, but the students and postdocs and the collaborators are those that contributed directly to what I presented today, as well as the funding sources for some of the studies that I presented. Thank you.
Thanks for that excellent talk about the secret lives of filters. We have time for questions. Please step to the microphone and state your name and affiliation, and Jeff will do his best.
Jeff, that was a very nice talk. Suresh, Daniela, Clarkson. So if you look at, so we did similar studies in Clarkson, and we found similar underperformance with respect to air exchange rates between what the facilities department think they're doing versus what we're finding. So glad to see consistency across all kinds of universities here. My question here is, how resilient are the HVAC systems to go up in MERV numbers? Because they're usually sized economically to just run what they're running right now, which is usually MERV 8. And I see there's a huge cost-to-benefit ratio going up to 11. And when we propose that, they're worried about the infrastructure behind it to run. The other question is, I see that the cost-to-benefit ratio tapers off after 11. If you can comment on that, that would be great. Thank you.
Yeah, so on your first question, you know, it's one of those things that's kind of truth, kind of myth about whether higher MERV is going to cause issues. And again, it comes to the design of the filter. So I've been, like some types of systems, like commercial rooftop systems, you really are limited to whatever the manufacturer has designed the system for. But other types of systems, you can often just put in a thicker filter rack and put in a thicker filter and have even lower pressure drop at higher efficiency. So some of this is just the resistance to change issue. And I can't comment on every university, and I can't even comment that much on the University of Toronto because kind of involved in the faculty association administration battle about this. But when I go up to mechanical rooms, and I'm not supposed to be doing this, I see things like filter bypass. I see, you know, gross problems that it's not a limitation of the equipment. It's a limitation of someone caring to do it properly. And so I really encourage what you're doing, the kind of in situ measurement, and then that works best if there can also be a feedback loop. So that you can say, hey, look, it looks like this is a ventilation issue. Maybe check the outdoor air damper controls, or this is a filtration issue. You know, use a gasket and make sure the filter there's no bypass going on. On your second question, you know, I often have said that MERV 11 ends up often being kind of a sweet spot in terms of price, performance, and so on. I think that, you know, the cost-benefit analysis are all based on, you know, different assumptions and so on. I feel like we really need some type of big meta-analysis that gets at those numbers directly. And I think some of what we're seeing is performance degradation, which is going to be more serious for some of the high MERV filters. So it could be that, you know, that there is actually diminishing benefits because they are more likely to degrade, or it could be we just haven't done the modeling right. And I don't know which of those it is.
Thank you.
Yes, Jeff, very nice talk. Jonathan Thornburg from Research Triangle Institute. I liked how you talked about the fate of particles that are collected on the filters and possibility of filters being a source. Mm-hmm. Could you comment on the collection of microbiologicals, specifically bacterial and fungal spores?
Yeah. So filters definitely collect lots of microbiological material. And this has become an issue. Early in COVID, I told people to be careful when changing filters because worried about, for example, a virus being there. I have to say, my opinion at this point is I still tell people to be careful, but I'm mostly doing it because I don't want to be responsible for someone getting sick. Filters definitely accumulate microbiological material. How active that material is really an open question. If you talk to people who change filters for a living, they report something they call filter fever, which is when they change filters at certain times of the year in certain buildings, they're more likely to get some type of respiratory virus. Hard to know. I've never seen that in any of the occupational health literature or otherwise, so just that anecdotal story. But the comment I'll make is where we see filters be very microbial active is when they get wet. And filters sometimes get wet because they're supposed to be upstream of cooling coils, but sometimes there are situations where water pools and wets the filter. And then you don't need to, again, be an aerosol scientist to see, you can count the growths on the filter. And so certainly we've extracted, and lots of other people have extracted all kinds of different fungal and bacterial DNA, as well as RNA from viruses from filters. And so we know they have the biological material there. What there's much less data on is whether that has the ability to convey infection or be active.
Thanks, Jeff. Sarah Henderson, VC Center for Disease Control. I appreciate your very clear message of use a good filter, make sure air goes through it, and change it often. But I also want to highlight that there's a tension there with your message around equity and the potential role of filters. So the First Nations Health Authority in British Columbia has a HEPA in air cleaning lending program, and it's a bit of a nightmare logistically. Mm-hmm. Just wondering if you can comment on that tension.
Yeah, so I think I have two answers. The first answer is we have to do a lot better on both the, helping people understand how to use filters well, as well on the technical side. We're doing some work right now, and can we optimize the performance of filters so that they last much longer, for example, by using them when they'll provide the most benefit. So I think there's a few dimensions to that. But I think the broader issue is, 90% of the cost of ownership of most portable filters is in the replacement media. And that's really expensive, and they're already expensive to begin with. And even the do-it-yourself ones can be quite expensive if you put good filters in place. So it's a real issue. But I guess I look at it in two ways. The first way is, from an economic perspective, we should just be giving filters away and making sure, people have access to the replacement filters. From a public health perspective, I can't imagine, even if I'm wrong by an order of magnitude in the benefits to cost, it's still beneficial to do that. And then the second comment is, again, I don't want to sound hopelessly naive, but so much of the problem we have around indoor air issues is we have not done a very good job messaging some of these issues. And so in my daughter's classroom, I think the HEPA filter lasted 3 days before the teacher turned it off because of noise. And I think that, we really have to do better on the engineering side, but also do a lot better on the messaging and get people more engaged with how these filters are used. But on the equity side, we should just be providing them. Especially in somewhere where the healthcare costs of not providing them are just so huge. And I'm really trying to shift the argument from not the cost of the unit itself, but the cost of not providing it.
I'll just add that in BC, we are looking at making these things medical devices, which would allow filters to be, a prescription, essentially. Thank you.
Yeah.
Hi, Jeff. Gedi Mainelis from Rutgers University. Thank you so much for your insightful talk. I was wondering if you could comment a little bit, let's call this on mobile indoor spaces, such as trains, for example. As an example, we recently got some filters from regional trains to look at and test, and let's say, related to the previous comment, they had to be handled with care.
Absolutely.
Because there is so much, all kinds of stuff accumulated. So I was wondering if you would comment or provide some insights where you see that part of this field is going, and the potential upgrades they could do, and what else these mobile spaces could do to improve air quality.
Yeah, I think that in many cases, we have not paid a lot of attention to the filtration systems in mobile environments, and I think there's enormous benefit that can come from doing that. But I also think there is this huge benefit in being able to use them as samplers, as you're talking about. And I think where we have to improve a lot is the kind of, like right now it takes months typically between when I get a filter, get all the metadata on it, and then it takes a while to get the material off of the filter, and then we have to process it chemically or biologically or whatever we're doing. And then it's like, oh, yeah, you had an exposure hotspot a few months ago, and that's not very useful. So we have to think about ways like rapidly. So I've proposed before, never been successful in getting funding in doing, very simple types of stuff, imaging, acoustic analysis, stuff you could do almost with handheld instruments right on site. And it wouldn't give you a very precise answer, but it would say, hey, this filter is different from its neighbors. We should do stuff. And one thing that I hope those with more biological chops than I would think about are things like staining. And just rapidly staining a filter. And I know it doesn't give very specific advice, but it tells you some things about how much biological material is there, and is it worth kind of delving further. And I think that's a direction we should think about for mobile environments.
Thank you.
Ann Middlebrook, NOAA, Boulder, Colorado. I was wondering about if you have some sort of program to give away filters. Wildfires are a very big health impact. In addition to the virus that we had recently, then there's dust storms in Arizona. Would you recommend having different types of filters for these different types of potential health issues?
So I think there's a lot of value in simplicity. And so I almost feel like let's enable good filters and people can use them. And I think where we need a lot more than on, overwhelming people with choices or, oh, this is this threat, I should use this filter, is how to use a filter well. And that's where I'd like to see more attention paid. And if you look at, I mentioned there was 70 or so articles on the health effects of filters. I think there's less than 10, maybe even less than 5, that actually look at the behavioral and the use issues around portable filters. And so that's where I think we need attention much more than on, so getting filters to people is part one, helping them to use them well is part two. And if we succeed in that, I'm really happy, and then maybe we can get more sophisticated.
Hi, Dr. Siegel. My name's Brian. I'm a student at Drexel, co-advised by Dr. Shannon Capps and Michael Waring, which I guess makes you my grant advisor. I was just wondering, what do you think ASHRAE standards need to do? What do you think they do well to cover, what do you think ASHRAE standards cover well in regards to filters, and what do you think they need to do to better improve their standards?
So I think the biggest need is for a rapid in situ filter test, so that when filters, you put in a filter, and if these contextual issues are important, or you put in any type of air cleaner, you can immediately see what the benefit is. And that's where I think we need the most attention right now. I also think, and I've said that ASHRAE was talking about, should we have a 52.3 for residential filters, because they're kind of different. And I made the argument, hopefully successfully, that we need a guide about how to use filters more than we need another filtration standard. So I think those are the two things, in situ tests and guidance on how to use filters.
Hi, Shannon Capps, Drexel University. This is really compelling that changing the filters regularly is necessary. I'm wondering what you think about the probability of aerosol science informing a way to regenerate filters in place. It seems like it would solve a lot of the problems that have been raised.
Yeah, so there is several filter products on the market that can either be regenerated, sometimes with heat, sometimes with washing of various kinds. And the challenge is, to my knowledge, none of those are higher than about a MERV 8 or so. And so I think that there's a lot of promise in that idea. But I think that the practical challenge is what drives the filter. I mean, filters have unfortunately become a commodity at this point. And so if you have if you have like the main cost of a filter for a big commercial building is the service call of the people to come out and change it. And so if you can find a way to do that regeneration in situ, and I don't have any great ideas, but there's lots of very smart people out there, you have to find a way for that to happen that doesn't involve the service call. And I think that's the real challenge. But I think there's been a lot of talk of that kind of thing. Some people have proposed like biologically active filters that kind of self-clean, some other ideas like that that I think we need further development and testing. That sounds interesting. But I don't know of any practical technologies that have a relatively high efficiency.
Okay, let's thank Jeff again.
Thank you.